Hey class, Adam Ward here, starting our third lecture about open channel hydraulics. And in this lecture, we're going to focus on sharp crested and broad crested weirs. There'll be two lecture videos for today. This one focused on sharp crested and the next focused on broad crested weirs. Two learning objectives for today. One is that you can explain how we used the energy equation for both of these scenarios and some of the simplifying assumptions that we make. And secondly, I want you to be able to use the equations we derive to estimate discharge based on standard measurements you would make near a weir. Okay, so we're going to talk about weirs today because this is one of the ways that we measure discharge in open channel flow. These are incredibly common, and the idea here is that we're going to force the flow in a natural river, like the one you see on the right-hand image. We're going to force it to go through a constriction, and we're going to know quite a lot about the geometry of that constriction. And the ultimate idea here is that if we know something about the depth of water in the system and the shape of the weir, we can estimate discharge. Now in this video, we're going to talk specifically about sharp crested weirs. That's what's pictured in both of the photographs here. And what makes it a sharp crested weir is you'll notice that they're both extremely narrow or sharp in the direction of flow. When we look at broad crested weirs, we'll see that they're several feet or several meters long. So they're stretched out along the channel, where these are one cross section in width. Okay. They come in lots of shapes, shown along the bottom of the screen: rectangles, triangles, trapezoids, and at the end of the lecture, we'll look at more complicated shapes as well. So the idea of working with a sharp crested weir, is that we're going to be able to measure the depth of water above the weir. That's labeled with a capital H in this image, and we're going to use that knowledge to estimate discharge. One of the things you'll notice in this cross section is we're showing this drawdown that happens over top of the weir. So we are not actually going to be able to, we're not actually interested in the depth of water that I've just illustrated in purple with the sad face. We're interested in the depth of still water back behind the weir. Now, why does that drawdown occur? Well, in order to get all of that discharge over the weir, we're actually having to accelerate the fluid to get it to go through. Just a couple of other notes. Downstream of the weir is a free jet. And in its optimal configuration, a sharp crested weir looks like I've highlighted in that red circle with the star there. You get a really sharp corner and a free jet that sort of launches off of it, as opposed to a condition where water would sort of weep down the front of that weir. You really want it to separate from that sharp crest as it goes over. So again, our goal is that we want to measure the depth of water above the weir, back where the water is still, and we're going to use that to estimate discharge. Okay, so how do we do it? These two images that are sort of faded, we'll leave in the background. You've seen those on previous slides already. So the idea here is that as we approach the weir, we have approximately uniform velocity on the left-hand side of the image, and we accelerate and change that velocity profile as the water goes over the weir. Of course, the energy grade line would be up above the water surface, and it would be a distance of v squared over 2g above. And if we looked at a cross-section or a frontal view on the right-hand side, you can see we're thinking about a trapezoidal weir in this case. For our derivation, so you can see how this is using the energy equation, we're going to focus on just one flow path. And so I've drawn a flow path in dark red over on the profile. And of course that would correspond to some slice if we were looking at the frontal view of the weir shown on the right-hand side. Okay, so what are some of the key definitions or variables that we're going to need to describe our system? We're going to think about a flow path that starts at point A, that is an elevation of ZA up from the bottom. We're going to envision a depth of water when it flows, just at the time it flows over the weir, being lowercase h down from that still water surface. So that vertical line drawn in orange on both the profile and frontal views, That's how far down from the water surface we actually are. We'll envision that there is some area that's represented by this measurement. So this flow path represents that hatched red area would be length multiplied by height, or L times dH. We'll think about point B, the second point, as being right at that spot where the free jet starts to occur. So just as the water flows over the weir. On the next slide, we're going to take this diagram and we're going to write the energy equation linking point A and point B as our next step. So here we go. Energy equation from A to B. And so this should look pretty comfortable to you. This is actually the Bernoulli equation. So we're assuming that there's no head loss as we go across that weir. And of course, that's probably not true, but we're at least assuming that it's minimal. And some simplifications we can make here. We can define those vertical coordinates on the basis of the height of the weir, PW, the height of water over, capital H, and then how far down we are from the water surface, lowercase h. And so just to remind you, this is just sort of a roundabout way of defining elevations. So you're starting from the surface, hatched at the bottom there, going up by PW and H, and then down by lowercase h. Similarly, we can simplify out for a free jet, a pressure of 0. Now, I didn't break it out, but you could calculate the pressure at point A using our hydrostatics equation, gamma HCA, or gamma HC, as it were, gamma HA. You can similarly adjust the way you're describing the elevation for point A to be a function of PW and capital H. And all of that to say, what you end up with when you simplify the energy equation down is what I've written here. V2, so the velocity of that flow path as it goes over the weir, is equal to the square root of 2 times g multiplied by the quantity of how far down you are from the water surface, lowercase h, plus the velocity head on the upstream side. So what you've done here is you've calculated the velocity for this one slice in the vertical dimension. And so for that little slice or strip, discharge is area times velocity. If we want to know the total discharge over the whole weir, we simply integrate that. So the discharge over the weir, capital Q, is the integration of that V2 term multiplied by dA, or the incremental area that it represents, the cross-section of that strip in this case. So we can take that generic form and actually derive some equations by doing the integration. So in the case of a rectangular weir, this is probably the easiest. The width is constant. Right? So what we had called this generic script L before is the value B. It's the width of the weir, and as you move up and down in the vertical dimension, that width doesn't change. So we can go ahead and fill out our integration here, where that first term is the velocity that we calculate or derived on the previous slide. That second term is the incremental area that it represents. And so the area of every strip is the length times the change in height. And if you go ahead and integrate, you get a fairly ugly looking equation here. Discharge is equal to 2/3 times the square root of 2g multiplied by the width b, and all of that multiplied by the quantity of h plus v1 squared over 2g to the 3/2 power minus that velocity head upstream, also raised to the 3/2 power. So this is both a sort of complicated looking equation, but it's also not particularly handy to us, because not only do we need to know the geometry of the weir, B, we also need to know the depth of water flowing over it, capital H, and we need the upstream velocity. So one of the ways that we simplify this is to say, well, the depth of water over the weir should be relatively small compared to the height of the weir. That's something you might control in design. And the upstream velocity should essentially be a stilling basin. So V1 equals to 0. And if you make those two assumptions, this equation simplifies to something much more manageable. And we really like this from a management perspective because the data collection is pretty easy. Width of the rectangle, no problem, I built it. And height of weir over top h, so we just need to measure water depth. And that water depth is one of the things that we've been logging as a discipline for many years. We're very good at automating that. It's a simple measurement. Now, the problem is those aren't very good assumptions. This is a river or a stream. Of course, the velocity upstream is not equal to 0, and seldom is it the case that you have an extremely tall weir with an extremely small amount of flow backed up behind it. So, while those aren't great assumptions, we did get rid of V1, and so rather than put it back, we have a different strategy. We want to keep the benefits we derived, meaning keep the simplification from getting rid of V1, but we want to correct this equation. And so what we've done in this case is we add this coefficient, and in this case this is called a rectangular weir coefficient. So C for coefficient, W for weir, and then R for rectangular. And this coefficient is a function of the weir geometry itself. So it's a constant 0.611 plus 0.075 times that ratio of height of water, H, to height of weir, PW. Now, you might say, well, what's the difference here, right? You had an equation that worked, you simplified it, and then you made it more complicated again with this coefficient. But what we've done in that process, yes, we've made it an empirical equation now, but we've gotten rid of the need to measure velocity, which is something that's much harder to do and harder to log in an automated way. And all of it can now be described by the geometry, B and PW, and the depth of water, capital H. And the process we went through on this slide is typical of everything that we'll do for weirs. So we go through this derivation process, then we simplify away terms that we don't like or things that we don't want to measure, and then we add an empirical coefficient to correct it and approximate the behavior that's more accurate. So for example, if we switch to triangular weirs, the world gets more complicated because the width of that little incremental strip, labeled as a script L in red, changes as you move in the vertical. And so you can describe that, right? The distance that you are down from the top of the water surface or up from the pinch point of that weir can be described geometrically. It's 2 multiplied by capital H minus lowercase h times the tangent of theta over 2. So that's fine. We can do the exact same steps that we've done in the past. So we'll integrate that equation, then we'll simplify some terms and add a correction factor. And what you get is what I've written here in black. Discharge Q as a function of a weir coefficient for a triangular weir times 8/15 times the tangent of theta times the square root of 2g multiplied by that depth over weir at capital H to the 5/2 power. And again, that weir coefficient, we can try to approximate it in an empirical way. Similarly, there are often tables that you would look this up in. So what weir coefficient to use on the y-axis as a function of h on the x-axis. And you'd see curves for different values of theta. So a theta for 90 degrees in the lightest blue, and as that contraction gets narrower, that weir coefficient gets higher. Ultimately, when the weir has enough flow going over top of it, that angle starts to fade away and you find yourself at a value of about 0.58. Now, the question you might ask then is, why would you have different angles? Why don't you just pick an equation to describe 90 degrees or 45 degrees? Who decided we should have these differences? The trade-off you have is sensitivity. So as that theta gets smaller and smaller, meaning that triangle or that notch gets narrower and narrower, you make a bigger height difference with changes in Q. In other words, the smaller value of theta you pick, the more sensitive your weir gets to those low flows. And so one of the reasons that you might go for a narrower value of theta is to get really good resolution at really low flows. Now, in order to balance that with high flows, we'll commonly design what are called compound weirs. So here's a simple compound weir where you've got a little triangular notch in the middle, and that triangular notch is very narrow. So at the lowest, driest flows, we get good resolution. But when the flows get much higher, you have a large cross-sectional area and it behaves more like a trapezoidal weir. And so we can take the equations we would describe for triangles and rectangles and trapezoids, and we can basically add them together and combine them for these more complicated shapes. Okay, so what I wanted you to take away from this video was 1, what is a sharp-crested weir? 2, I wanted you to see that the way we use this to measure discharge is by relating the depth of flow upstream of the weir to the actual discharge passing over the weir. And I wanted you to see the energy equation is what backs this up. So if you just look these equations up on the internet, what you find are the empirical versions that have these coefficients. And you might think that it had no physical basis in that case. That's not true. In fact, there is a very clear physical basis, and then we've chosen to simplify part of that equation away and put part of that back as an empirical. That root 2g, for example, someone didn't magically come up with that coefficient. That's part of our derivation. All right, folks, so that's sharp-crested weirs. I'll be back with one more lecture video where we will talk about broad-crested weirs. Thanks, everybody, and I'll see you soon.